Thank you to Dr. Vicky. I would like to invite the second moderator, which is Professor Komang Dharmawan, Ph.D. Professor Komang is a teaching staff at the Department of Mathematics in Udayana University. He holds a bachelor in ITB Mathematics, a master in UNSW Applied Mathematics, and a doctorate in UNSW Financial Mathematics. Professor Komang, his areas interest is in optimal control theory, financial mathematics, risk theory lecturer at Udayana University since 1988.
Good morning, ladies and gentlemen. I'm here to work with, collaborate with Professor Junji Shikata from Japan. Before we start, let me introduce Professor Shikata.
Yes. Can you see my slide?
Professor Shikata, before we start, let me introduce yourself. Ladies and gentlemen, Professor Junji Shikata is a lecturer and also a dean of the Faculty of Environment and Information Science, Yokohama National University. He received his Ph.D. In 2000 in mathematics, Osaka University, Osaka, Japan. From now, he's been the researcher in the Faculty of Environment and Information Science, Yokohama National University. Okay. Today, he will present his research interests including cryptology, information theory, theoretical computer science, and computational number theory. Okay, Professor, your time is yours. Please, you can start.
Okay, thank you. Can I share the slide? Can you hear me? Can you hear me? Okay, so.
Yes.
Thank you. Can you see my slide?
Yes.
Okay, thank you. I'm Junji Shikata from Yokohama National University, Japan. It is a pleasure for me to give a talk as a plenary speaker of this conference. And currently, I'm Dean of Faculty of Environment and Information Sciences, Yokohama National University, Japan. Today, I would like to give a talk about group testing and its application to cryptography. And first of all, let me apologize that I cannot join the conference on site because of some reasons, including coronavirus regulations of my university. Okay, so I'd like to change the slide, but sorry. Okay. First, let me introduce group testing. This is algorithm or protocol which has been developed mainly in bioinformatics. Group testing is a method to detect some special items called defectives, bad ones, among many whole items with a small number of tests than the trivial individual testing for each item. And applications of group testing include screening blood samples for detecting disease and detecting clones having a particular DNA sequence, and efficient examination for infectious disease, and constructing cryptographic protocols, and so on. And this group testing technique was first considered by Dharmawan. He considered group testing to efficiently detect blood samples contaminated by syphilis during World War II. And since then, group testing has been advanced as a research area of computer science, such as bioinformatics. So, okay, by the next slide, I will explain the group testing concretely. Suppose that there are several bad elements in a large finite set. So in this illustration, there are 8 items, and numbers 3 and 4 are bad ones, and the other ones are good. So the purpose is to detect the bad ones, 3 and 4. So in group testing, we suppose that the following test is possible. So we can choose any subset of the whole set. In this illustration, number 1, 2, 4, 5 are selected. And then test. The result is as follows. If the result is good, all of them are good. But if the result is bad, we can say that at least one of them is bad. So, for example, suppose that there are 8 cups of tea, and there may be a poison tea among them. And the purpose is to specify which one is poison tea. And the group testing is very simple in the context of this example, because we prepare a cup, and we mix the 4 cups from number 1, 2, 4, 5, and mix. We examine the mixed tea, and if poison is detected, we can say that there is a poison among the 1, 2, 4, or 5. And if we select 3, if we select, for example, 7 and 8 and mixed, and we test the mixed tea from 7 and 8, of course, the result is good. So we can say that there is no poison in cups of number 7 and 8. So this is an example of group testing. And the purpose is that we want to test with small number of tests than individual testing. The purpose of group testing is to specify all the bad elements by testing subset of full set as a bad, such that the number of testing is smaller than that of individual testing. Okay, so if we check 8 cups where there might be a poison, we need to test 8 times if we perform individual testing. But so if we can construct elegant algorithm, we can specify all poison T less than 8 tests. And group testing can be classified in the following 2 types. The first one is non-adaptive group testing. And in this group testing, all subsets to be tested are selected beforehand. And the second one, adaptive group testing. In this testing, a subset to be tested is selected after knowing the result of the previous test. So in general, adaptive group testing is efficient than non-adaptive group testing. So this is an example of adaptive group testing based on binary search. So in the previous example, we can construct the following algorithms. First, we define group 1, which consists of 4 sets and test. Because 3 and 4 are bad ones, the result is bad. So this is first test. The second one is we divide the group 1 into 2 disjoint subsets. In this slide, we define the first subset as which consists of 1, 2, 3, 4. And the second one consists of 5, 6, 7, 8. And because 3 and 4 are bad ones, the result of group 2-1 is bad. But the second group testing output good result. So we can specify the bad one is in the subset of consisting of 1, 2, 3, and 4. In the next group testing, we divide the first group into the following 2 sets. The first one is 1 and 2, and the second subset consists of 3 and 4. And we test again. And because 1 and 2 are good ones, the result is good. So we eliminate these 2 items for the candidate of bad ones. So we can specify 3 or 4 bad ones. And the final test checks individually 3 and 4, and the result is bad for both cases. So we can output with 3 and 4 bad ones. So, of course, we don't need to perform the test 8 times in this case. Okay, so more generally, the group testing, adaptive group testing, this is a very powerful tool, is like this. Subset to be tested is selected after knowing the result of the previous test. And AZT, adaptive group testing, is performed in several stages while estimating the number of defectives is not necessary in some AGT with a non-fixed number of stages. So, for example, known algorithms include binary search, as I explained, and rake and winnow algorithms, Bayes algorithm, and digging algorithm, which is a variant of binary search, and so on. The point is optimality, I mean the number of tests. So there is a known proposition like this, and for integers n and d, so let m be the minimum number of tests to detect the defectives, I mean bad ones, from n items. Then M is estimate in the interval of this L. So this means that the almost optimal number of tests is the order of the logarithm of n, and these multiply. So, for example, AZT mentioned above, binary search is near optimal, but the dominant term is multiplied by 2. So from this estimation, we can conclude that the digging algorithm is almost optimal, but it requires a large number of stages. But we focused on the minimum number of tests. We can say that digging algorithm is nearly optimal. Okay, and so this is explanation for adaptive group testing. But next, I would like to explain non-adaptive group testing. So this is a more serious scenario because usually suppose that n is number of false set and u is number of tests, then non-adaptive group testing is designed by U times n matrix Z, binary matrix Z, and rows are indexed by the test, and the columns are indexed by element of the false set. And the element is equal to 1 means the test I investigate the element J. So if we define D disjunct, so this is sometimes called cover B, but in this context we define as a D disjunct. G is said to be, matrix G is said to be D disjunct if the sum of any D columns of G does not contain any other column. Okay, this is sometimes formalized as cover-free family. We take arbitrary D plus 1 subset of false set, and the union of D subset cannot cover the other subset. Okay, this is the same meaning. And so if we can design this type of matrix, we can construct efficient group testing, non-adaptive group testing algorithms. And so this is an example of disjunct matrices. The first one is one disjunct with 5 rows and 10 columns. And the second one is two disjunct matrix with 9 rows and 12 columns. Okay. And so by this slide, I would like to explain how one disjunct matrix works to detect one bad item. Suppose that number 5, ID 5 is defective. So based on this matrix, we perform 5 tests. Okay. The first one is T sub 1 plus T sub 1, mixing the contents of ID 5, 6, 7, 8, 9, 10. Okay. Of course, because we suppose the ID 5 is defective, the result is bad one. And the second test consists of mixing ID 2, 3, 4, and 8, 9, 10, because corresponding entries are all 1. And of course, 5 is not included. The result is good. And we perform 5 tests. And so actually, we focused on good result because we can eliminate these items from candidate or bad ones. So we eliminate all 2, 3, 4, 8, 9, 10, and 1, 6, 7, and so we delete like this. Then ID5 is remain, so we can specify ID5 that is bad one. By designing this one disjunct matrix, we can specify at most one bad ones. And so this is a known result for disjunct matrices. F is the minimum number of rows for the disjunct matrix with n columns. Then the purpose is to estimate minimum number of rows. So F is the purpose of targeted estimation. And we already know that asymmetrically, F is like this, d to the 2 multiplied by logarithm of n. And so this is asymptotic upper bound, but we want to know the tight lower bound in a non-asymptotic way. And we have the following result, namely, and the last one is just a conjecture, not proved yet. So, but for example, some result. The first and second are not tight. And the 3, this is conjecture by Eldish et al., is true for less than or equal to 5. And if there is some condition, the conjecture is true with constant rate. But in general, F is not known for arbitrary N and D. This is a purely mathematical problem. I also would like to introduce application group testing to cryptography, which is my recent project supported by Japanese government. The purpose is as follows. So in future, the number of IoT devices is increasing, and there will be an enormous number of devices connected to the network. So in such a situation, we need to realize efficient communication or data transmission in an authenticated manner in the network, including 5G and beyond 5G. Beyond 5G means, for example, 6G or 7G. Usually, so we consider message authentication code as a lightweight cryptographic primitives for message authentication. However, traditional one-to-one authenticated communication by map is not enough to resolve the problem, because one-to-one communication leads to the enormous number of data in the network. Actually, the number of tag is the additional information to be used for checking validity of the message data. So checking the integrity of the data. So this is usually added to the original data. And the purpose is to compress tags without losing security. So this is a trivial communication in the network. And if there are many IoT devices, the number of transactions is proportional to n. And of course, the data size is proportional to n. The purpose is too complex to reduce the data for many IoT devices. So our idea is as follows. The idea is to compress the many data at the aggregation node. So, but the problem is that we can trace a device that has sent invalid data from the aggregate tag in general. So if receiver confirms the data is not correct, then we cannot specify the data sent from which IoT device sent. So we cannot use the data because we cannot specify which data is invalid. So the idea is to use group testing in this network, okay? And so okay, let me skip the slide. And this is algorithm. So each IoT device sends data to aggregation node, and the aggregation node compress data and send to the receiver using network. But the point is that to use group testing here, and the resultant data is compressed. So let me skip. Okay, so this research project was supported by Japanese government from 2017 to 2020, and so we published several papers about this result, and eventually this result is summarized as a proposal to ITUT, which is international standard. ITU is a specialized agency of United Nations for Information and Communication Technologies, and this aggregate message authentication code with group testing was accepted in September 2020. Okay, so this is conclusion. So group testing is interesting mathematical structure. Actually, group testing has important applications, including screening blood samples for detecting a disease, efficient examination for infectious disease, and constructing cryptographic protocols. But the optimality of non-adaptive group testing, I mean optimal design of disjunct matrices, is an open problem. Application in viewpoints of application to cryptography, group testing can be used as a building block for constructing lightweight authentication protocols. Our authentication protocol using group testing became an international standard in 2020, and this research was supported by Japanese government. And solving the open problem about the disjunct matrices leads to achieving optimal compression of data transmitted in authentication protocol, maybe in future for beyond 5G, 6G, 7G. And this is I think, interesting topic of mathematics and its application to information science. That's all. Thank you.
Okay, that's all talk from Professor Shikata. Give applause to him. Okay, thank you, Professor Shikata. Okay, it was very interesting talk from you. And then there are many technical terms actually, but it's all right. And then, okay, before we start the discussion, let me summarize a little only the application of the group testing. Okay, the group testing is a method to detect some special items called defectives among many whole items. With a small number of tests, then the trivial individual testing for each item. The application of group testing includes screening blood samples for detecting a disease and detecting clones which have a particular DNA sequence. Okay, in this discussion session, we, because the time is very limited, and we invite only 3 questions. Okay. So ask the question to Professor Shikata. Okay, while we waiting the question from the audience, Professor Shikata, would you please explain the application in real life? Okay, and I mean in the real life, what is the actually what are you doing in using group testing? Yes.
Okay. Sorry. So you mean real application?
Okay. Yes. In ordinary life. Ordinary life. In everyday life.
Okay.
In everyday life.
So, yes. Okay. So. Okay. So in a recent real applications of group testing, so we, as you can see, the third one, efficient examination for infectious disease. And so as you know, we are we are required to detect, for example, the real application include coronavirus infection detection. So I hear that some country applied group testing to specify coronavirus infection. So because, for example, some samples are medically mixed and tested, and so group testing mechanism could be applied. So, and then so we can specify people who are infected coronavirus infected. Then we can successfully specify with small number of tests than individual testing. So I think this is a real application of large impact of group testing to coronavirus infection detections. Is that okay?
Yes. Okay.
It's not in Japan.
Yeah, for me, it's okay. Is there any other question? Yes. In the back.
Thank you for the chance given to me. I'm Putri from University of Mataram. The topic is very interesting, but one question that I want to ask to Mr. Junji is, I have heard that in fraud detection, for example, we can use like via hyperplane approach. It is a study in analysis, but I saw that in your presentation you use matrix approach. And what I want to ask is that how, which one is more effective? I mean that in your presentation, you use some iteration, right? So but in using hyperplanes, we just take some subspace of a space, a whole space, and yeah, maybe you can give me some explanations related to which one is more effective. Thank you.
Okay, thank you. So actually, to resolve the open problem, I think there are several approaches to do it. And so one is algebraic approach to analyze binary matrix. The other one is, as you mentioned, the graph theoretical approach by using hypergraph. So yes, so it is very interesting, and so this program is very classical one. But if we integrate the recent graph theoretic approach and so other ones, it may be possible to open the door to the new problem and resolution to the open problem. Thank you.
Okay. Is there any other question? Okay. Please introduce yourself.
Thank you for the. My name is Ratna Sari Widyastuti. I am from Udayana University from Mathematics Program Study. Prof. Junji, I have to ask you two questions. The first is how we can make the subset from the finite set, and the second is possible to apply the group testing in the infinite set. Thank you very much.
So I'm sorry, I cannot clearly hear the question.
How would you define subset from finite set? Is it okay?
Yes.
Okay, so how to select subset, right?
Yes.
Okay, so it is just the core mechanism of constructing group testing. So in adaptive group testing, so after knowing the result of the previous test, how to select the next subset is actually the core algorithm construction. So from this viewpoint, we introduced, for example, a binary search. It is trivially divide the subset to disjunct more subset. So this is a binary search. So if you can come up with some good, elegant idea, then you can reach on the new group testing algorithm. So actually, how to select is core point of constructing adaptive group testing. And non-adaptive group testing, actually, this leads to directly design the disjunct matrix. So actually, how to select subset is in a core point of constructing group testing.
That's okay?
Okay.
Thank you. I think time's up, and then I'll give applause once again to Professor Shikata. Thank you for
Thank
your
you.
time, Professor. And then hello from Bali.
Thank you. So
Hope
from
you can
Japan,
come sometime to Bali.
I'm very glad to join the conference. Thank you.
Okay, thank you. Thank you very much.
Thank you very much.
Okay, that's all talk from Professor Shikata. I hope this talk is very helpful for especially from student or lecturer from mathematics. Okay, thank you very much.